Right, so some of these graphing questions might seem a little bit tricky, but once you've done a few, you'll find that it should get much easier and you'll be able to recognize the tricks. So the more you do, the better. Let's have a look. Question 1. We have a graph of velocity over time. And the question is, which one of the following graphs best represent the variation with time t of the acceleration a? The best thing to do with these graph questions is to actually try and answer the question without looking at the answers first. And if you can, then finding the answer will be easy. Let's have a look. Here we have a velocity time graph. You need to look for the fixed points first. Now, by a fixed points, you mean places where it's easy to tell what's going on. Here we have a nice fixed point where the velocity is equal to, sorry, not the velocity, but the acceleration is equal to 0. How do we know that? We know that because the gradient is equal to 0. It's flat. Okay, so whatever graph you choose, the point in the middle should go through the center. Now, let's have a look at any other fixed points. What's happening at the intercept with the y-axis? At the intercept with the y-axis, what you can see here is that the gradient, okay, is very hard to do gradients on this program, but the gradient is really steep. So let me tidy that up. So what we got here is a graph that shows that at time t equals 0, the velocity is at a maximum, but also the acceleration is at a maximum because that's where the gradient is steepest. But it's not only at a maximum, it's also a maximum in the minus direction. So it will be, if we sketch a quick graph of what it should look like, plus, minus, okay, you would have here at time equals 0 a maximum minus acceleration. Now what happens at the next fixed point, which would be this time here, t max, okay, at that maximum point. If you look at the gradient again, it's also at a maximum. Okay, that's more or less done. But it's a maximum, it's increasing, so it's positive. So what you've got is at that point there, you've got a maximum value for acceleration. Okay, and this is time in seconds. So we know the center, where the gradient is equal to 0, is going to be equal to 0. And we have these other 2 points. This one, a maximum acceleration here, and a maximum acceleration here, but this one's minus and this one's positive. Now let's have a look at what's happening in between. Is the gradient changing? Well, it is, because as you move across, as time increases that way, you can see that the gradient is getting flatter. The gradient is decreasing. Now the gradient is equal to the acceleration. So the gradient in this case is decreasing from the minus maximum value to the 0, and then it is increasing on this side. You can see it's getting steeper. So it's increasing up until there. So it looks like we have our answer. The answer is A. Because, well, have a look. What's B like? B assumes a flat acceleration, which means that the acceleration is not changing. It's a constant value. So you would have expected the gradient here to have been always the same, and it's not. And then let's have a look at the other graphs. This one would have been correct, but this acceleration is positive, and this is quite clearly negative because that gradient is decreasing. And this one's just nonsense because, well, you know it's not this one because your gradient is flat. Question 2. The graph shows the variation with time t of an acceleration of an object. And the question is, the object is at rest at time t. Which of the following is the velocity of the object at t equals 6 seconds? Now, you should remember from what we covered in class that if we think of our cake, Again, here it is. We have gradients. So the velocity, gradient of velocity time graph will give you acceleration. The velocity of a displacement time graph will give you voltage. But then the other way around, the acceleration, to find the velocity from the acceleration, you would work out the area under the graph. Okay, so for here, we need to work out the area under the graph for the first 6 seconds, which is a really nice triangle. Very easy to work out. So what we've got there is we've got 6 times, that 6 is the time, times, let's have a look there really carefully, it's 14. 14 divided by 2. Okay, and that gives us 42. But hang on a minute, that answer is not in the options. So what you have to do in this case is you have to take the closest one. So the closest one would be 36. Okay, so in this one we've got a ball being dropped from rest at time t equals 0 onto a horizontal surface where it rebounds. So a ball drops on a surface and then bounces back. The graph shows the variation of time t with speed v of the ball. Now, which one of the following best represents the point at which the ball just loses contact with the surface? So let's consider the journey in stages. A ball is just dropped. This is our surface. The ball just hits the surface and then it bounces. So you've got a point, this point here is the point at which it meets the floor, and then you've got the point where it leaves the floor, right? And then you would have like a fourth stage where it bounces up, and because there's energy losses, it will bounce up to a lesser point. Hang on, I'm drawing and thinking at the same time. Not easy. So here we go. I'll say that again. So you've got stage 1, the ball is up in the air and it's just dropped. It drops and it's, imagine that point just when it's about to touch the floor, right? So that's stage 2. And then your stage 2 is it touches the floor and then it's released. It bounces, okay? And then it goes up again. And, right, in order to try and figure out which part of the graph A, B, C, D applies to these stages, then we just need to think about the velocity at each stage. So let's think about the velocity here. The ball has left your hand and it's at 0, isn't it? So it's just when it's starting its journey. Now it accelerates at 9.81, so its velocity is increasing. It's increasing up until a maximum. So at the point just before, if you can imagine a split second just before it touches the floor, its velocity would be a maximum. Okay, so the ball then hits the floor, and you can always imagine like this ball squashing and, deforming elastically. It will just get totally squashed, and then it will stop for a microsecond, and then it will revert back to its shape, and then it will be released back up again, which is shown here. So in this part here, what we've got is a sudden and very quick slowing down to v equals 0. So from the point that it touches the floor to it being totally squashed, the velocity becomes 0. And for that tiny amount of time, it's 0, but then suddenly the ball goes back to its normal shape and it increases up to v max again. Okay, and then it will decelerate, because here it's at a maximum, and it will decelerate at minus 9.81. Okay, and then it will go back to here, and of course, because of energy losses, there'll be a few issues as well. Because of energy losses, this v max is a little bit less than this one, and this height will be a little bit less than that. Okay, so now let's go back to the graph and let's see if we can make sense of it. This journey here, where the ball the ball's velocity starts at v equals 0 up until a maximum would equate to this part of the journey, right? So from here, v equals 0 to v equals max. Now, this A to B would be at that point, from the point that it has maximum velocity to the point that the ball is squashed and that split second where it stops. Okay, so that would be there. That would be B. Now C is where it unfurls, it goes back to its original shape, and it goes from velocity 0, a squashed ball, to a normal ball shape, and it's got Vmax, and that's like just as it moves back up. So that's exactly what the question is referring to. Which of the following best represents the point at which the ball just loses contact with the surface? So that would be C. Okay, and then just out of interest, it's worth noting that D would then be the fourth part of the journey, which is this deceleration up until a 0 again. Okay, so anyway, just to sum it up, just in case it comes up again, from V0 to Vmax, we have journey A. From this Vmax to V equals 0, that would be B. From V equals 0 back to being launched to Vmax, that would be C. And then back up to this position would be D. Anyway, the answer to the question was C. Question 4. The diagram below shows the variation with time t of the velocity of an object. Okay, so the question is about the acceleration. So what does the acceleration time graph look like? Well, as you know, the acceleration is equal to the gradient of a velocity time graph. So this in effect is asking you what is happening to the gradient of this graph. So I'm going to draw the axes underneath here so we can figure out what's going on. So here in this section, the gradient is actually equal to 0. So that means that on an acceleration time graph, for that period, for that section, you would have a line going through the x-axis like that. And then what happens here? Well, in that slight curve there, it immediately goes down to some value there. And then the gradient is constant. It's flat, isn't it? So it suddenly goes like that. And how do I know it's going down here? It's a minus. It's a decreasing gradient. So, and by decreasing, I don't mean a decreasing gradient. I mean the velocity is decreasing. So we have a minus acceleration. So your graph should look like that. So if we have a look at the options, we can see that D is the answer. Okay, so let's have a look at this question. The graph below shows the variation with time of the acceleration A of a spaceship. Now already you should start thinking, if it's an acceleration time graph, what can I do with this graph? Well, the only thing you know is that the velocity is equal to the area. Okay, so what does it ask? The spaceship is at rest at t equals 0. The shaded area, what does it represent? Well, you know by now that it's equal to the velocity. So A, is it equal to the distance travelled? Well, no, it can't be. Is it equal to the speed? Well, velocity would be the most appropriate at this level, but yeah, sure, acceleration is equal to the speed as well. The gradient of a speed time graph would give you acceleration, as well as a velocity time graph. A speed time graph would as well. But let's just leave it there for now. Let's read the other options just in case. C, the rate at which the speed of the spaceship changes. Basically, the rate of change of speed. Now, you guys should remember the definition of acceleration is the rate of change of velocity. it could just as easily be the rate of change of speed. That's just as correct. Okay, so what this is saying is, does it represent the acceleration? No, because it's an acceleration time graph. The axes, the actual readings, represent acceleration. And then D, the rate at which the acceleration changes. So no, because that would be the gradient. I think we mentioned this in class. The gradient of an acceleration time graph would be the rate of change of acceleration. So indeed, the answer is B. Okay, an object is dropped from rest from a point several hundred meters above the surface of the Earth at time t equals 0. The object strikes the ground at t equals t, capital T, and air resistance is not negligible. Now, it's a bit unfair, this question. I've given it to you a little bit too early, but it'll get you thinking. So don't worry if you find this one too hard. I haven't taught you enough to do it properly, but let's see how well you do. Which of the following sketch graphs best shows the variation with time t of the speed v of the object? So as a ball falls, if you can imagine, I'll just sketch out 3 stages in the journey for you. The first one would be just at that point where it's released, and the velocity is 0. Now what should happen if there was no air resistance is that this ball would accelerate continuously until it hits the floor with an acceleration of 9.81. So that would be A, okay? But unfortunately, it's not that easy because the air resistance is in fact a factor. So how does air resistance or having air resistance change this graph? Well, the acceleration slowly reduces, okay? So it starts off with an acceleration of 9.81, but as it goes through and the air pushes up on the ball, it slows it down. You end up with with a force that acts upwards to try and balance out the weight down. And you actually get to a point called terminal velocity, which we'll look at in the next chapter, where the two forces, the weight and the air resistance, actually balance out. So eventually the ball will hit a point where it becomes constant. So what actually we're looking for is graph A, but with the acceleration slowly stopping so that the velocity doesn't increase linearly anymore. It peters off until it gets to a constant velocity. Okay, so the correct answer would be B, like that. Now, your ability to do this question relies on you having knowledge of this from last year, or maybe some stuff we did in grade 8 with parachutes. You might remember playing with parachutes in grade 8, but you probably don't remember why. So don't worry about it, because we will cover this in length in the next chapter. 4 cars, W, X, Y, and Z, are on a straight road. The graph below shows the variation with time t of the distances s of each car from a fixed point. Which car has the greatest speed? Now, interesting, because what this is telling you is that the direction is not important. So it's displacement time graph. What's the relationship between speed and displacement time graphs? S over t gradient equals velocity. Okay, so which one has the highest gradient? It's W. Okay, so the answer is A. And it is a bit tricky because you might think, oh, it's a minus, but it doesn't matter if it's minus velocity. The fact is, the speed, the magnitude is the only important thing. So it would be W. It would be A. Okay, so we now have another velocity time graph. Okay, and the question is, which area represents the distance covered as the speed reduces? So as the velocity goes down. So what we can see here is, here the velocity is increasing, here it's reducing, here it's constant, and here it's reducing. So the only areas that you need to worry about are while the speed is decreasing. So we're only worried about S1 and S3. S2 is the distance covered while the speed is constant. So the total distance would be equal to S1 plus S3. Let's have a look at the options. Okay, so if we look at the selection of options, we can see that C is the correct answer. Question number 10. Familiar graph, but this time it will be a different question and different axes in fact. The diagram below shows the change in velocity over time. This time, what is the area between the line of the graph and the time axis? So basically, what does the area under the graph represent? Is it the average velocity? No. Is it the displacement? Yes. Okay, so the answer to that one's very easy. It's B. So this is a tricky question. The graph below shows variation with time t of the distance moved by a car along a straight road. During which time interval does the car have the greatest acceleration? Right, so you've got distance moved and time. The velocity, or better still, the speed, can be found from the slope of these graphs. So if we find the slope at A, at the beginning of A, compare it to the slope at the end of A, you can see that there is a change in velocity because there's a change in the slope. And a change in the slope, delta V or V minus U, same thing, over T, is actually an acceleration. So in this stage, there is quite a considerable change in velocity. But the same is happening here. And you can see that from here, this is relatively, it's still at a small angle, but the change from that slope to this slope is quite a large one. Okay, so here we have acceleration as well, because we have a change in velocity over time. And then here, during C and D, the gradient pretty much stays. This is a little bit flatter, but the gradient stays pretty much the same. So on the one hand, we can get rid of C and D because there isn't much going on there. We need to make a decision. We need to decide, where is the change greater? Is it from here to here or from here to here? And I think probably there's a bigger difference in that time period B. So I would say the answer was B. Now this is a horrible question because there isn't actually that much difference between A and B, but the answer is in fact B. Okay, so this is a familiar question. A ball is dropped from rest at time t equals 0 onto a horizontal surface from which it rebounds. Which one of the following graphs best shows the variation of speed with time t from the time t equals 0 to the time the ball leaves the surface? So we've kind of looked at this before in a previous question, but we have, again, we have the first situation, which is right at the beginning. The ball has a velocity equal to 0 and it accelerates, so its velocity increases to a max. So it can only be A and B, because C and D don't show that. And then what happens? Well, first you've got to show that sudden decrease in velocity as the ball gets squashed. So you should see the velocity then drop. So it has to be A. Okay, that's showing that drop there. And it also shows you what happens when it leaves the ball, when the ball leaves the floor again and starts coming back up. So the answer is A.